Thank you, Mr. Chairman, ladies and gentlemen. This is a bit similar to yesterday's presentation. It is once again numerical simulation, but the structure is completely different. Yesterday it was more human story. Today it is about the aircrafts. You can see from the list of authors that it is a joint effort, not only from Serbia, also our friend from Croatia is here. But originally this was a project, a joint project between Switzerland and University of Belgrade. Actually, we were asked to simulate possible crack growth, fatigue crack growth in a certain component. And that was in order to explain or to understand how this component behaves in presence of cracks. So we will see about the part and the component itself, about the damage, material, load, some repair, and then assessment. So first I will present you photographically what was found, what had been done, and then I will present numerical simulation to see what we can assess. It is about the exhaust nozzle and a certain part that we call inner sleeve. You can see where it is. And this is the model that will be used later on. This particular structure here is so-called patch. I will explain later on. Then we can see a model itself already, later to be used. This is inner skin. This is outer skin, and certain honeycomb structure in between, not very important from the structural point of view. And then again, very important part is this solid piece of metal. Once I said the metal, we can maybe jump to the material itself. It is an alloy made of titanium. Although it is the aircraft structure, it's not the one that we are used to, not a structural component. Actually, this one is so-called Beta 21S. This is a special alloy with the beta phase of titanium. As some of you probably know, it is metastable. Actually, it's not stable at the room temperature unless it is stabilized by some alloying elements like vanadium, molybdenum, and not aluminum. He has counter effect, but it is added to increase ductility. So the point is that operating temperature is relatively high, that there is some oxidation which produces also some damage. So what we should keep in mind are also these relatively high tensile properties and relatively low but still acceptable, in a way to say, fracture toughness and ductility properties. So to go back to this slide about the damage, there were cracks detected and some, I would call them amateur attempts to repair it. So just welded to stop further growth of crack, which was not successful, as you can see. This is, by the way, the part we are talking about. So this initial try to repair the damage was not really successful. You see this? Now for the loading, you can see basically something that we took as granted because it was given by the manufacturer, documentation. It is about thermal loading. Temperature, you can see it is at the outlet ambient temperature, and then as the input or inlet it is 433 or something close to 400, so there is a big temperature difference, and that produces thermal stresses. And you can see the distribution of the stresses. So this is load input. To go back to this service experience, bad experience, in the sense that cracks were noticed in many components. In this case, you can see also in these two cases a good old way to stop the crack, but not successful in this case. Like in Liberty Bell, drilling the hole with the idea to reduce or to transform stress intensity to stress concentration, but it didn't work, as you can see. Probably because this is fatigue. In Liberty Bell it was just impact. So all these cracks you can see schematically 1, 2, 3, 4 different ways. It's very complex, and it was a very complicated task to simulate numerically. Just a few more examples about this cracking. Whenever it was tried with the elements, another cracks appeared, so not a good idea. Then some calculations which was also provided to us by the manufacturer, not very relevant, but just to show how this analysis looks like. And then again, this final attempt to solve the problem with patch insert. So the idea is to cut out the whole area with the damage, and then to use some old parts and cut out the patch of the old part, which was still sound and without defects, without damage, and then to weld it. I hope you will not be more frightened now to fly after seeing that. This is not a structural component anyhow. You can see now a few weldments which were also unsuccessful in stopping the crack. Actually, new cracking appeared. You see it here, as well as here. As metallurgists would say, very nice cracking. And then this repair procedure, weld quality check, and some micrographs. Also hardness distribution, all of that okay, but we still had cracking. So now I come to the numerical simulation. The first model, there were 3 of them, I will present 2 of them. The first model was just to see how one development, which resembles this problem in reality, can we get actually, can we simulate crack growth for this single development? And we really did get crack growth along development. But anyhow, yes, you can see it also here. Anyhow, for our analysis, we were using certain properties. There is still some controversy about these parameters. They have to be checked. But anyhow, this is how we can get this crack in the model number 1, and a few nice colored figures to get to this one. It's very interesting. You can see how it really grows. Let me see if we can get it once again. Yes. This is modeled in ANSYS, and that is model number 1. That was one weldment, not a patch. So this model here will be about this patch. You can see it here, and in better view here. This ellipse here actually represents the crack as modeled in ANSYS. You can see total number of nodes, and now you can see how crack propagated. So all the way here and then down there. To get results like this, it looks simple once we are looking at it, but it took about a couple of weeks of hard work and different models to get crack growing at the same time this way and that way, which is the case in reality as well. This is the view from the back, so that crack also went through the thickness. And this is yet another simulation. You can see crack growing that way and this way. You will also see that once it gets up to here, it will slow down in this direction, vertical direction, almost stop, and still will propagate in this horizontal direction. Okay, now I think even better view from here. Yes. And as simple as it looks now, as I told you, it took several weeks to get something which strongly resembles reality. Now I don't have here number of cycles and so on. This is still kind of checking up. Even this company that ordered this simulation is not very happy to publish everything, but they allowed us at least to show you how it is possible to simulate even very, very complex crack growth. So, conclusions. This cracking mechanism is very complex. As I showed you at one slide, it could go 4 ways. This conclusion is not very much important, but slightly different materials can be modeled as one, but this is what is very important. Estimated number of cycles, we can estimate number of cycles when crack is moving through the solid skin, even after applied patch. This is very important because that patch turned out to be the best way to try to stop the crack, and even if it's not successful, we still can estimate number of cycles, and this is how we can control the phenomenon. So, at the end, you can probably feel like Enrico Fermi, and so do I, and thank you for your attention.